Hey all, this is Derek and this is section 9.6, exponential and logarithmic equations. And for the exponentials and logs, we're going to see two flavors within each of those categories. So starting off with exponentials, we'll look at like bases or one-to-one property of exponential functions. And basically all this is saying is if I have an exponential, if they have the same base, then those exponents, I'll write that a little bit bigger, b to the x equals b to the y, that can only be true if x equals y, if those b's are the same. And so for solving exponentials using the one-to-one property, if I have something where maybe it's not quite the same base at the moment, but I can do something sneaky and make it the same base, then I can dump those bases, set the exponents equal, and solve. So it doesn't always work, but when it does, it's a lot easier than the alternative. So for this first one, we got 3 to the 4x equals the square root of 3. The square root of 3 can be written as an exponent of 1/2, because remember, square root is the same thing as 1/2. So then what that means is that 4x has to equal 1/2, because they're both 3 to the something equals 3 to something else. And then from there, we'll just, I would think of it as multiplying by 1/4 is probably the easiest way to see that. And then those are canceling, and x is 1/8. For that next one, you can probably kind of see there's a 5 situation going on. So 5 to the x, 1 over 125, I could write that as 1 over 5 cubed. And then to bring that exponent up, I can basically do the opposite of what we normally do, which is write it as a negative. And so 5 to the negative 3 is the same thing as 1 over 5 cubed, but now I have those like bases, and so I can see that x has to be -3. Okay, for number 3, we have 4 equals 32 to the x minus 1. So 4 and 32, those both can be written as base 2. So instead of 4, I'm going to write that as 2 squared, and instead of 32, I'm going to write that as 2 to the 5th, and then that's still being raised to, so multiplied by x minus 1. And then we have 2 to the second equals 2 to this stuff, so we can drop those and get 2 equals 5x, and then distributing there will be -5. Let's add our 5 over, so 7 equals 5x, and then dividing the 5 on both sides, I'll write the other direction, x should be 7/5. This next one, so we got 9s and 27, so that 9 I'm going to write as 3 squared, and then that little tiny exponent is 3x minus 1. 27, I'm going to write 3 cubed, and that x minus 5. And so now, since I have 3 to this equals 3 to that, I'm going to set those equal. So I will distribute as I go. So basically doing that. 2 times 3 is 6x. 2 times 1 for -2. 3x and minus 15. So subtract our 3x over here and get 3x will be left. Add that 2 over here, and that's going to leave -13 on that side. Divide it out. X equals -13/3. Okay, so then the second flavor of exponential equations, we will use logarithms to solve. And so where this will come in is something as simple as 3 to the x equals 4. What power do I raise 3 to get 4? I don't know. There's nothing clever I can do with 3 and 4 like I just did with those last 4 problems. So with this, I would have to use some other method. And what that other method is going to be is right here using logarithms. So first thing I want to do, actually I have log both sides as the first thing I want to do, but if it's not simplified as basically just down to an exponential raised to some power equals a number, we want to get it simplified first. So here, this is 3 times 2.8 raised to the x, they wrote inside, equals 12. So I'm going to divide that 3 over first, just because it's going to make my life easier here in a second. So now I have 2.8 raised to the x, 12 over 3 would be 4. And then what I want to do is I'm going to use logarithms. I'm going to log both sides. And we've done this idea before. When we had x squared, we would root both sides. When we had a square root, we would square both sides. So we're basically just using the inverse operation to get at the unknown. So once I've logged both sides, what that lets me do is apply property 3 from the last section, and now I can bring that exponent down front where I can get at it. And I got log 2.8 equals log 4. These are just numbers, so I'll divide that over, and x equals log 4 log 2.8. And this one asks for it to 4 places. Sometimes it's 3 in the directions, sometimes it's the exact value, so just be careful to read the directions on the problem. I'll show you some of the exact ones coming up. And when I threw that in the calculator, I got 1.3464 to 4 places. Okay, so here, again, an exponential. I can't write 9 and 2 with common base, so I will just log both sides of this right now as I write it down. And then we'll bring the exponent down front. I have 2 choices here. I could distribute and solve, or I could just divide it over. I am going to go with just dividing it over. And then from here, we're asked to find this to 4 decimal places. So this is where I would let your calculator do most of the work, is pretty much after this point. So if we just do log 2, and then carefully close that parenthesis, divided by log 9, and make that a number. So now we're at 3x minus 1 equals that number on my screen. I don't want to write all that out, so I'm just going to go plus 1, adding that over, and hit enter. Cool, got that. And now I need to divide by 3 and hit enter. And so I got to write a lot less and not type very much either. And it looks like this is 8, 5 to 4 decimal places. So once you can kind of let your calculator, just do your order of operations and let the calculator keep track of most of those decimals. This next one, so this would be, we would add that 7 over, because again, we want to get the exponential part by itself. And then let's divide over the 6. So I have e to the x equals 3. So for this one, you could just change it to log form and you would be there. I'll show it as logging both sides just to kind of show these steps on why that other would work. So here I can bring the exponent down, same as before. And then ln e, remember this is 1, because that's the same thing as log base e of e. So what do I raise e to get e would be 1, so that drops out. And then you're just tossing ln3 into the calculator. And on this one, it is asking for the decimal approximation, so that was 1.0986. Okay, and then these next couple of examples are asking for the exact solution, and they'll do that sometimes with problems involving e, so that just means we're going to write the answer in terms of e. So this first one, let me write this in the other order just because I feel like it looks nicer with the variable on that side. And I'm going to isolate, so I'll divide out that 7. E to the 5t equals 2. We could natural log both sides there. Bring that exponent down front. Then I have 5t, let me write that better. 5t ln of e equals ln of 2, and then ln e, remember that's 1, so that drops out, and then that lets me divide over the 5 on both sides. So here, t would equal ln 2 over 5, and then that would be the exact form, so that's what they're looking for there. This one, so we add the 6 over, and we get e to the x minus 5 equals negative 14, and that is a DNE. And the reason that's a DNE is if we think about what an exponential function looks like, this would just be an exponential base 2.7-ish and shifted 5 to the right. So basically it would look something like that. And then negative 14 would be somewhere down here, would be where y equaled negative 14. Those are never going to cross. So if you see an exponential equaling a negative, after you've simplified everything, along with that shift, if it's negative, it's a D and E every time. Okay, so then on to log equations, and we're going to see the same two ideas here. These first ones will be using the one-to-one property. So what we want to do is get each of these down to a single log, and then we can, well, because we can exponentiate, it allows us to drop the logs and then set it equal and solve. So here we have a minus, so this would be, let me come over here with it, log z plus 2 over z equals log 79. And so since I have basically, log of x equals log of y with the same base, x has got to be y. So that lets me set z plus 2 over z equal to 79, and then I can solve. So I will multiply both sides by z. That gets rid of that fraction. And now I have z plus 2 equals 79z. We'll subtract over the z and get 2 equals 78z. Bring that up here. And then divide the 78 on both sides. And that would be 1 over 39 equals z. And then with log equations, we do have to check for if we're taking log of a negative number. Remember, our log graphs look kind of like this. And again, this is after they've been simplified, so if there's anything where we have to move it around, we've done that already. So the domain for a log is 0 to infinity, so we have to watch out for negatives. And it's not negatives precisely, it's when we put them into the argument, do they make a negative number? And you'll see in a later example what I mean by that. But here, if I put in 1/39, this is positive and this is positive, so everything's good. Okay, for these ones, they're already log equals log, so that means I can just set those arguments equal to one another and solve. So here, I'll bring that 7x over, and that's going to give me 0 equals x squared minus 4x, factoring x minus 4. So just for this quadratic, I get solutions of 0 and 4. But again, what matters is when I put them back in the log. So even though x is 0 is a solution to this, if I put it in here, ln 0, that is not part of the domain, because what we just saw on the last page, the domain for logs is going to be 0 to infinity, not including 0 because that's the asymptote. So that one is extraneous, but the 4 looks good. And not just because it's a positive number, but because when I put it in, this becomes 28, and so does this side, and it's 28 and 28, they're both positives. So that one is our legit solution. Similar exercise here. So this would just be negative 7x equals x squared minus 8x. I add that 7x over, and I get 0 equals x squared minus x. Okay, so then I can factor in x out. So far just basically like this one. And we get x equals 0, and then x equals 1. And so very easy to go, okay, x doesn't equal 0, cool, that one doesn't work. And then 1's a positive number, so that must be the real answer. Except if you look, when you plug that in, you get natural log of negative 7, which again, that would give you, that's not an actual thing because our domain is from 0 to infinity, so it doesn't work on either side. And so this one's a D and E. So just because it's a positive number, again, the thing that matters is what happens when you plug it in. Okay, and then last in this section is log equations. And these ones I just did had logs in every term. These ones are going to have logs and then a number. And so there's, again, a couple of ways of doing these as well. I'm going to show it where we write it as a single log and then switch to exponential form like we did a couple of sections ago. So, and same thing applies, we want to get this as simple as we can first. So if there's anything going on outside the log, we want to make sure we isolate that. And now that I've done that, I can do that exponentiate where I say 3 to the second makes x, which pretty much then x is 9, and 9 doesn't make that negative, so all is well. Here, let's subtract that 6 over because we want to isolate. So 2 log 6x plus 4 equals 2, and then we'll divide the 2 on both sides. So log of 6x plus 4 equals 1. And then remember when there's nothing there, there's that invisible 10 is a common log. So 10 to the first equals 6x plus 4. Subtract the 4 over. 6 equals 6x, and x equals 1, which does keep this positive, so that is the solution. Okay, for this one, we have solve the equation for x and answer exactly. So again, this is where we'd have answers involving either natural logs or e's. We will isolate the log. So that's going to give us natural log of x minus 7 equals 5. Again, think of the invisible e right there. So e to the 5th equals that argument. Oops. And then we just need to add the 7 over. So e to the 5th plus 7 equals x. And then that's our exact form. This is pretty similar. We'll subtract the 2 and get 9, and then natural log of x equals 9. Cool, we'll divide the 9 over. Natural log of x equals 1. And so invisible e to the first equals x. So e to the first is e equals x. And then these last few we're solving, we'll write it as a single log, switch to exponential form, and then just kind of see where we got to go. So this is log base 3, that's a minus, so this one will be a division, equals 1, and then we're going 3 raised to the 1 makes the stuff inside, and x plus 3 over x minus 1. Fractions, always good to clear those, so let's bring the x minus 1 up on both sides. And then we'll have, let's see, 3x minus 3, those cancel, equals x plus 3. This one's linear, so we want x's on one side, numbers to the other. So bringing that x over is going to give me a 2x. Bringing the 3 over is going to give me a 6. And x equals 3. Checking my answer, 3 plus 3 will give me 6. 3 minus 1 is still 2. So those are both positive, so this is okay. Here, this time it's a plus, so similar, but this time it'll be a multiply instead of a divide. So log base 4 of x, x plus 6 equals 2. So then we're going 4 to the second makes the argument of the log. So 4 squared equals x squared plus 6x. That's a 16, so I'll move it over here, get my 0, and I'm doing that because this is an x squared. And so you can see this one was coming up quadratic, so that's why I want to get it set to 0 so I can factor and solve. So x plus 8, x minus 2, I get a negative 8, which I'm suspicious of, and x equals 2. Sure enough, when I put that 8, the negative 8 in, it's negative all over the place. That's no good. I put 2 in, it stays positive, so that one is our solution. And in terms of the solutions, it could be they both work, neither one works, only one works. You just have to check and see. And then this last one is basically the same. Here we would have log base 2, x plus 1, x plus 3 equals 3. So we could go 2 to the third makes the stuff inside. So 2 to the third would be 8 equals, and then we would FOIL. So x times x would be x squared plus 3x plus x plus 3. Or 8 equals x squared plus 4x plus 3. It is quadratic, so let's bring this 8 over. 0 equals x squared plus 4x minus 5. And multiplies negative 5, adds to be 4. So it sounds like x plus 5 and x minus 1. So my possible solutions are x equals negative 5, which does not work, and x equals 1, which works great.